we shall see some of the BJT applications and biasing in BJT. Before that, to know the relationship between alpha, beta and gamma, the gain of common base, common emitter and common collector. So the common base gain is alpha equal to del IC by del IE. The common emitter gain is beta equal to del IC by del IB. The common collector gain is gamma equal to del IE by del IB. So the relationships are alpha equal to beta by 1 plus beta, beta equal to alpha by 1 minus alpha, gamma equal to 1 by 1 minus alpha, gamma equal to 1 plus beta, and then 1 by alpha minus 1 by beta equal to 1. See these are the relationships between alpha, beta and gamma. Next we shall see how the transistor works as amplifier and switcher. So the transistor may work as an amplifier. BJT can work as an amplifier and switch we know. So to work as an amplifier to the transistor, we need to give a source resistance RS and input AC signal. Take V as the source signal and proper biasing voltage. The output is taken across a load resistance RL. So this is collector. So the collector current is IC, base current IB, and emitter current IE, and biasing in the output side is given. So the gain is output by input, gain voltage gain is output voltage by input voltage. So it is the output voltage should be higher than the input voltage to get sufficient gain. Next, the transistor, when it works as a switch, it should work in cutoff and saturation region. So to work as a switch, the diagram is like this. The emitter is grounded. Input we have a source resistance Rs and the input signal Vi is given, and output is taken across a load resistance and proper biasing is given. So the input is like this. So V1, this is at T equal to 0. So this is actually together. So this is the input voltage Vi, V1 and V2. So how it responds is, so here it starts and here it ends actually, but it is like, so it starts after some time and then reaches the peak after some time. So the curve is like this. So this time is, we have the different times here. So this is TD, TR rise time, T on time, storage time TS. Next we have TF the fall time and T off the off time. So what are these times? So we have the turn on time T on. T on is the delay between the leading edge of the input wave voltage and the time the collector takes to reach the 90% of the maximum value. So from the leading edge, from the starting till it reaches the 90% of the maximum value. So this is 90%. So this is 0.9 IC sat and this is 0.1 IC sat. Delay time, T delay. Three factors contribute to delay time. A non-zero time is required to change the emitter junction capacitance when transistor switches from off to on. A non-zero time is required for the minority carriers to cross the base and then reach the collector. Some time is required for the collector current to rise 10% of its maximum value. And then rise time TR. This is the time required for the collector current to increase from 0.1 IC sat. So here from 0.1 IC sat to the maximum to the highest value when Vi goes negative. Right to 0.9 IC sat. Turn off time is the time required for the collector current to decrease from IC sat to 0.1 IC sat when Vi goes negative. So T of time from the time it starts to decrease till 0.1 IC sat. Storage time, elapsed time from the trailing edge of the input pulse where IC just starts to reduce to 0 due to the saturation region. Fall off time, T of time it takes for the collector current to increase from IC sat to 0.1 IC sat. And finally the propagation time, Tp, is the time it takes for a transistor switch to respond to an input signal. It's called propagation time, TPD. And then we have the H parameter model for the transistor. We know the transistor works as amplifier. Transistor works as an amplifier. So the input voltage is Vi, the output voltage is V0, the input current is Ia and the output current is I0. Vi is a function of f of Ii, V0 and I0 is a function of Ii, V0. So the equations are Vi equal to H11 Ii plus H12 V0. I0 is equal to H21 Ii plus H22 V0, where H11 is Hi, which is equal to Vi by Ii, keeping V0 equal to 0. HR is H12, which is Vi by V0, keeping Ii equal to 0. HF is H21, which is I0 by Ii, keeping V0 equal to 0. H0 is H22, which is I0 by V0, keeping Ia equal to 0. So the equivalent model is, we have the input impedance Hi, input voltage Vi and input current Ii, and here we have HR, V0, input impedance, reverse voltage gain, and V0 plus and minus, and here we have the current source HF, Ii, and the output admittance, actually it should be 1 by H0. For simplicity of derivation we write it as H0 here. The output current is I0 and the output voltage is V0. So the equation is Vi equal to Hi, Ii plus HR, V0 and I0 equal to HF, Ii plus H0, V0. Same way we can draw for common emitter, common base and common collector with their corresponding input voltages and currents and their corresponding representations as HIE, HOE. The equations can be written for that. Then we have the stability factor for common emitter, base and collector. Stability S is equal to 1 plus beta by 1 minus beta dou IB by dou IC. We need to find the change in IB with respect to IC and find the corresponding stability factor S. So next we go for the different biasing. So first type of biasing in BJT is fixed bias. In fixed bias the diagram is like this. There is no emitter resistor. Here we have RC and base resistance RB. VCC is the voltage here. We have the capacitances and actually we remove the capacitances in the AC output signal, and also we have the output side capacitance here and we remove the capacitances and redraw the circuit because XC equal to 1 by 2 pi FC, so it becomes infinite when we go for the analysis. We'll write the KVL for the input side and output side and have the equations. So when we write the KVL for the input side, so here the current is IB, here the current is IC, KVL for input side will be like this. So it is VCC minus IBRB minus VBE, base emitter voltage here, minus equal to 0. So IB equal to VCC minus VBE by RB for fixed bias, and IC equal to VCC when we write KVL for the output side, minus VCC minus VCE by RC. VCE equal to VC minus VE, and VE is 0 since it's directly grounded, so it's equal to VC. VBE equal to VB minus VE, which is also equal to VB since there is no base emitter voltage. And then S is equal to 1 plus beta by 1 minus beta dou IB by dou IC. When we do dou IB by dou IC, there is no IC term and dou IB. So dou IB by dou IC is 0. So S is equal to 1 plus beta for fixed bias circuit. So next we go for the next type of biasing, which is emitter bias configuration. So emitter bias. So here this is similar to the fixed bias circuit, only difference is we have a emitter resistor RE here. Otherwise the circuit is same, the capacitances are removed. So here the current is IB, emitter current IE, collector resistance RC and its current IC, and VCC is here. Here are the KVL for the input side and output side, and we have the final equations. IB equal to VCC minus VBE divided by RB plus 1 plus beta into RE, and the output side VCE equal to VCC minus IC into RC plus RE. So these are the equations for emitter bias, and also IBE equal to IE RE. Stability factor S is equal to 1 plus beta by 1 plus beta into RE by RE plus RB when we do dou IB by dou IC. So the next type of biasing is voltage divider bias or self bias. So it is done by the voltage divider resistances. So this is RE, collector resistance RC, collector current IC, emitter current IE, and here we have the voltage divider resistances R1 and R2. So this is the base voltage VB, and VCC is here. So this is the base current I plus IB. Here the current is IB. So we need to find the Thevenin's equivalent voltage and resistance to do the voltage divider biasing. So we will have Thevenin's voltage VB equal to VCC into R2 by R1 plus R2. RT, the equivalent resistance is R1 R2 by R1 plus R2, and then Thevenin's equivalent voltage VT equal to VCC into R2 by R1 plus R2. We will get, on writing KVL for input side, IB is VT minus VBE by RT plus 1 plus beta into RE, and we write KVL for the output side, VCC minus IC into RC plus RE equal to VCE. Also we need to find the stability factor for voltage divider bias, which is S is equal to 1 plus beta by 1 plus beta into RE by RE plus Thevenin's resistance RT. So we go for the next type of biasing, which is collector to base bias. So here we have the circuit like this, collector to base bias, and also we have a modified collector to base bias with a small difference. So here The base resistance RB is here and the collector resistance RC is above the base resistance connection RC. Here VCC, emitter resistance, with emitter resistance is modified collector to base. We'll see first without one. So this current is IC plus IB. The base current is IB in VBE voltage. So on writing KVL, we get IB equal to VCC minus VBE divided by RB plus 1 plus beta into RC, and VCE equal to VCC minus IC plus IB into RC. The modified collector to base bias circuit is same with the emitter resistor RE included. So the modified one with the RE included, so we will get IB equal to VCC minus VBE by RB plus beta into RC plus RE, and VCC minus or VCE equal to VCC minus IE into RE plus RC. The stability factor for the collector to base bias S is equal to 1 plus beta by 1 plus beta into RC by RC plus RB. So these are the types of biasing and how transistor is used as amplifier and switch. Thank you.